Welcome to another lesson on trig identities. In this lesson we'll be looking at the double angle, half angle, and reduction formulas. Again, just very similar to what we looked at in the last lesson. We just need to know what are the identities, what do they look like, can we recognize them when we see them, and then just how do we use them to simplify expressions or to compute exact values. And again, with all these, we're going to add a few more identities as we keep going, but the purpose of these identities in terms of computing values is to give us, without the identities, we can only do 30, 45, and 60 degree angles, or angles that have those as reference angles. So by having these other identities, it allows us to compute more and more values for different angles. So like in the last video, we looked at how you can compute the sine of 5 pi over 12, right? So 12 is not one of our unit circle values, but using one of the identities, we were able to actually compute it. So again, adding these identities just give us more tools sort of in our tool bag of things that we can do to compute these exact values. And it also just allows us to simplify more and more expressions. And then we'll look at how we can maybe prove some at some point. But so it's giving us, it's adding more tools into our tool bag of things that we can do. So again, we will add a few more in there in following videos. I will point out that all the identities we talk about in this lesson can be found on the identity sheet that's posted in class in the lab manual, and then. So anything that we talk about here, you don't have to actually have memorized for a test or anything like that. But again, you should be familiar enough with the formulas, with the identities, so that when you see them on the page, when you see them on in some sort of problem, you recognize this is the type of identity I need to use. So with that said, let's go ahead and list through what all of our identities are, and then we'll look at some examples. All right, so the first set of identities we call double angle identities. And again, just looking at our expression here, we have the sine of 2 theta. I do need to go back and edit out that part in the previous one. So notice the 2 here. So this 2 is 2 times theta. That's why we call it a double angle identity. So say we had the sine of 60 degrees. Well, 60 degrees is really double a 30 degree angle. So we could compute the sine of 60 degrees using the double angle identity, where we would compute 2 times the sine of 30 degrees and cosine of 30 degrees. We don't have to, because we know sine of 60 degrees. But again, it's something that we could do. So again, we could think of the sine of 60 degrees as 2 times the sine of 30 degrees times another cosine of 30 degrees. So if we know 60 degrees is root 3 over 2, we'd get the same thing if we computed this right side. Again, but our goal is to expand the types of angles that we can compute these values for. Sine of 2 theta is equal to 2 sine theta cosine theta. That's our double angle identity for sine. For cosine, it's a little different. We have 3 options to pick from. So cosine of 2 theta is equal to cosine squared theta minus sine squared theta. It could also be written as 1 minus 2 sine squared theta, or it could be written as 2 cosine squared theta minus 1. And those 3 versions, just if you knew the first one, you could get the other 2 using Pythagorean identity that we talked about a couple lessons ago. So they're all the same thing, just different formats, so that it just allows us to use one or the other a little bit more easily given different problems. But again, just be familiar with those if you see them in any particular problems as we move forward. And then for tangent, so the tangent of a double angle, the tangent of 2 theta, is equal to 2 times the tangent of theta, just a single theta, so 2 times the tangent of theta divided by the quantity 1 minus tangent squared theta. So those are the double angle identities. Again, you don't have to have those memorized, but you should be familiar with them as you keep doing your homework and practicing through the lab manual and stuff. You need to know when you see them in a problem, you need to know this is the identity that we're talking about. The next group of identities, we'll call them the reduction identities. So reduction means to reduce, right? So we are reducing the power on our trig function. So if we have sine squared or cosine squared or tangent squared, we can rewrite it without the squared power. So we're reducing it from squared to just a single trig function. And we're actually able to write all of these very nicely in terms of just cosines. So sine squared of theta is 1 minus cosine of 2 theta all over 2. So it converts it from sine squared to a double cosine angle. Cosine squared theta is very similar. It's the fraction 1 plus cosine of 2 theta all over 2. And then tangent squared theta just combines the sine squared and the cosine squared to give us 1 minus cosine of 2 theta divided by 1 plus cosine of 2 theta. Again, the key there is it allows us to reduce from squared to just a single cosine, no more squared. And then the last group that we want to look at here are the half-angle identities. And again, say we needed to compute the sine of 15 degrees. Well, 15 degrees is not one of our unit circles. It's not 30, 45, 60, but it is half of 30 degrees. So if we wanted to compute sine of 15 degrees, we could using this formula. So, and the sine and cosines are very similar. So the sine of half of theta, or theta over 2, is equal to plus or minus the square root of the quantity 1 minus cosine of theta all over 2. And then for cosine, so cosine of theta over 2 is equal to plus or minus the square root of the quantity 1 plus cosine of theta over 2. So the only difference is the minus 1 minus cosine for sine and 1 plus cosine for cosine. And these formulas actually come off of they're just a different way of rewriting the double angle or the reduction formulas that we saw earlier. One of the difficulties with these half-angle identities is that we have to pay attention to the quadrant that your original theta over 2 angle lies in. What I mean by that is if, say, theta over 2 is originally in, so say sine of whatever angle you're taking is originally in the fourth quadrant. Well, if it's in the fourth quadrant, half of it's going to put it into the second quadrant. And so whether sine is in the fourth or the second quadrant changes whether it's positive or negative. So we have to play around with that a little bit, and we'll look at some examples here. And the reason we have the plus or minus, if you remember in algebra, if you take the square root of both sides of an equation, you get plus or minus. And so it comes out in the algebra from rewriting the reduction identities. We don't have to worry about this, however, when we do tangent. With tangent of theta over 2, there's actually two ways we can write it. We can write it as 1 minus cosine of theta over sine of theta, or that would be the same thing as rewriting it as the sine of theta over 1 plus the cosine of theta. And again, those two, just the variation is just based off of a little bit of algebra simplifying and the Pythagorean identity. So again, just be familiar with those. You don't have to have it memorized, but you should be able to recognize it when you see it and know how to use it. All right, so let's look through a few examples. So let's suppose that we know that we have some angle theta, and we know that theta is in the fourth quadrant, and we're told that the sine of theta is a negative 4/5. So again, sine of theta is negative 4/5, and theta is in the fourth quadrant. We want to find the exact values of sine of 2 theta, cosine of 2 theta, and tangent of 2 theta. Now, there's several ways that we can do this. We could, and any of them would work, but I just want to use the identities for each of these, just so we can kind of see how the identities work. So let's first write out the identities we want to work with. So we know the sine of 2 theta will equal 2 times the sine of theta times the cosine of theta. So in order to compute this, I need to know the sine of theta and the cosine of theta, which I'm already given the sine of theta. Okay, so we just need to figure out what cosine is. If we did cosine, so cosine of 2 theta, remember there's 3 options that we can use to write this one. And so it might be best if we pick whichever one's easiest, and I already know what sine is, and so one of the identities was 1 minus 2 sine squared theta. So I can already compute this without doing any extra work because I already know what sine theta is. Again, to do the sine of 2 theta, the first part of the problem here, we need to know cosine, so we'll come back and do that one here in a minute. But here, if we did cosine of 2 theta is 1 minus 2 sine squared theta, we already know sine and we could compute that pretty easily. We're going to have 1 minus 2 times, well, we know sine is a negative 4/5, and that has to be squared. So that's going to be 1 minus 2. 4/5 squared would be 16/25. And so we have 1 minus 2 times 16/25. You just multiply the 2 in the numerator. So it'd be 1 minus 32/25. And to compute this to a whole number minus a fraction, you need a common denominator, which is 25. So 25/25 minus 32/25 will turn out to be a negative 7/25. Okay, so that one's not too bad. We didn't actually have to do any special work for that one. And then let's look at tangent of 2 theta. So the tangent of 2 theta. The identity we had for this, it was that it was equal to 2 times the tangent of theta all over 1 minus tangent squared theta. Okay, now I'm going to go ahead and use the identity just so we see how it works, but a nice little thing about tangent is, remember, tangent is sine over cosine. Okay, and whatever goes in for your theta, for your sine and your cosine, is the same angle that you had for tangent. So since it's the tangent of 2 theta, I could also do this as the sine of 2 theta over the cosine of 2 theta. So you could do it as sine over cosine, and we're going to compute the sines and the cosines here in a minute. So we could compute that, but again, I just want to do it using the identity. So let me go back up here and finish the sine of 2 theta. So sine of 2 theta is 2 sine of theta cosine of theta. So that's 2 times sine of theta, which is a negative 4/5. And then we need to know what is the cosine of theta. Okay, so we're going to have to step to the side and do a little bit of work for this. So let's go back to what we were told. We know theta is in the 4th quadrant. So I'm going to draw my axes, my x and y axes, and I'm going to draw an angle in the 4th quadrant. So here's theta. It's between our angle and the x-axis. And then I'm going to form a right triangle. So I'm going to draw it from the end of my angle up to the x-axis. We have a right triangle there. And because this is sine, we know sine is the opposite over the hypotenuse. So I know I have a 4 and a 5, but it is a negative 4/5. And since it's negative, we're going to put the negative with the 4 because that's some units in the x direction to the right, and then 4 units down would put me at the end of my angle here. So the 4 has to be negative because we're going down, and then we have to find x, which we did as an example similar to this in the last video lesson that I did, but we're just going to do the Pythagorean theorem. So x squared plus a negative 4 squared has to equal 5 squared. So x squared plus 16 has to equal 25. That means x squared has to equal 9. And so x could be plus or minus 3. So which is it? Because that's going to be important, because depending on whether we do plus or minus here will change my answer to a positive or negative. Remember that the x coordinate, because we're going into the 4th quadrant, the x coordinate has to be positive because it's to the right. So we're going to go with the positive 3. So we're going to go with the positive 3. So that means that our cosine, which is adjacent over hypotenuse, has to be 3/5, and it's a positive 3/5. All right, so we know we have 2 times the sine times the cosine. That's 2 times a negative 4/5 times a 3/5. We know that the 2 has a 1. And so we're going to 1 underneath it, so we're going to multiply the 2 times the 4 times the 3. So 2 times 4 is 8, 8 times 3 is 24. And we know a 1 times a 5 times a 5 is a 25. So that's going to be a negative 24/25. So that's the sine of 2 theta. And we already did the cosine of 2 theta. So again, to do tangent of 2 theta, we could just take these two fractions for the sine and the cosine and divide them and simplify. And it would make life a lot easier. But again, I just want to work through the identity, which we have everything set up to do that. So we know the identity says the tangent of 2 theta is equal to 2 tangent of theta over 1 minus tangent squared theta. So in the numerator, we're going to have 2 times the tangent of theta divided by 1 minus the tangent of theta being squared. So what is tangent of theta? Well, go back to the triangle we drew before when we just did sine. We know from theta the hypotenuse is 5, the opposite side is a negative 4, and the adjacent side is a 3. So that means tangent of theta is going to be a negative 4/3. So negative 4/3 in both places. All right, so let's just simplify. That's all we got left. So 2 times a negative 4/3 is going to be a negative 8/3 over 1 minus, so 4/3 squared, a negative 4/3 squared is a positive 16/9, and that's being subtracted from the 1. And then to simplify all this, we still have the negative 8/3 in the numerator. In the denominator, we need to find a common denominator, so 1 is 9/9 minus 16/9. And that's equal to, again, another 8/3 in the numerator. 9 minus 16 would be a negative 7, so we have a negative 7/9 in the denominator. To divide a fraction, you multiply its reciprocal, so we have a negative 8/3 times a negative 9/7. The 3 and the 9 will reduce a little bit. So we're left with a negative 8 over 1 times a negative 3 over 7. So the 8 and the 3 multiply to give us a 24. And the 1 and the 7 just give us a 7. And because we had 2 negatives, this is a positive result. Now, just for kicks and giggles, if you were to take sine over cosine, just to check this, sine over cosine would be a negative 25th over a negative 7/25. The 25ths cancel, and you're left with a positive 24/7. So we still would have gotten the same thing had we done the sine of 2 theta over the cosine of 2 theta, and it would have been a lot easier. But again, I just wanted to show you how you can do it using the identity. Okay, let's repeat the same problem, but instead of doing the double angle identities, let's do the half angle identities. So let me go back to our triangle that we just drew. Again, we have this angle. It's in the 4th quadrant. We know the opposite side is a negative 4. We know the adjacent side is a positive 3, and the hypotenuse is a 5. Okay, that we found all that in the previous example. Okay, so we want to figure out the sine of theta over 2. And we know that that's equal to plus or minus the square root of 1 minus the cosine of theta all over 2. So in order to compute what the sine is, we need to know what's the cosine of theta, which is pretty easy over here. We know the cosine of theta is going to be 3/5 from our triangle. So we already know that part. And this is kind of the hard part next of where we deal with these half angles, is we need to figure out, is the square root going to be positive or negative? And so to do that, let's look at where the original angle is located. We know theta is in the fourth quadrant. So theta is in the fourth quadrant, which means if it's in fourth quadrant, we don't know specifically what it is, but that means theta has to be between 270 degrees and 360 degrees. That's just an angle in the fourth quadrant. If we rotated counterclockwise, it has to be between 270 and 360 degrees. Okay, those are the angles for the range of the fourth quadrant. But in this case, we want to compute the sine of theta over 2. So if theta is between 270 and 360, how do we figure out what theta over 2 is in between? Because remember, we're not trying to compute the sine of theta, we're trying to compute the sine of half of theta. So let's take my inequality here. 270 is less than theta, which is less than 360. And let's divide everything by 2. I'm dividing it by 2 because I want it to be theta over 2. Well, half of 270 is 135. So 135 degrees has to be smaller than theta over 2, and that has to be less than or equal to half of 360, which is 180 degrees. So what that means is if theta is in the fourth quadrant, which is between 270 and 360, half of theta has to be between 135 and 180, and that is in the second quadrant. Okay, so 135 degrees is like the 45-degree angle in the second quadrant, and then 180 obviously is the x-axis. So we're talking about some angle in the second quadrant. Now, what do we know about sine in the second quadrant, right? Sine is positive in the second quadrant. Okay, so we know, because of that, we know it has to be a positive square root. So we have a positive square root of 1 minus cosine, and we already said cosine was 3/5, and that's over 2. So all that's left here is to simplify this. So we're going to have the positive square root. 1 minus 3/5, you could think of this one as 5/5, so 5/5 minus 3/5 is 2/5, and that's over another 2, and then the 2/5, half of 2/5 is 1/5, so we're going to have the square root of 1/5, which the square root of 1 is 1, so you could actually rewrite this if you wanted as 1 over the square root of 5, but it's not necessary. All right, let's try cosine. So cosine of theta over 2. Okay, we know this has to be the plus or minus square root of 1 plus the cosine of theta over 2. Now, is it the positive or the negative square root? The cosine is the same, but is it the positive or negative square root? Well, going back over here, we know theta over 2 has to be between 135 degrees and 180 degrees, which puts it in the second quadrant. What do we know about cosine in the second quadrant? Cosine is negative, right? Because it's an x-coordinate. It's to the left of the y-axis. So this answer is actually going to be negative. So we're going to have the negative square root of 1 plus, and we already looked at cosine of theta up at the first triangle. It was 3/5. So 1 plus 3/5 over 2. So that's going to be the negative square root, and we know 1 plus 3/5, again, that's a fraction. 1 is a 5/5, so that's going to give us 8/5 over 2. And if you reduce 8/5 over 2, you're just going to divide the 8 by 2, so you're going to have 4/5, which would be a negative 2 over the square root of 5. Okay. So the last one we want to look at is the tangent of theta over 2. Now again, because it's tangent, I could rewrite this as just sine of theta over 2 divided by the cosine of theta over 2 and just use the two answers we found, and it'll actually make life super easy. But I just want to go ahead and do it using our identities. For the identities, we can pick whichever of the two options we want. I'll just go with the first one. So I know tangent of theta over 2 has to equal 1 minus cosine of theta all over the sine of theta. Okay. Now, that means we have 1 minus, cosine of theta we already said is 3/5. So 1 minus 3/5 in the numerator. And in the denominator, it's the sine of theta. So we haven't actually figured out sine of theta yet. So going back to our triangle, sine is the opposite over the hypotenuse. So sine of theta is going to be a negative 4/5. And so we just need to go through and simplify it. 1 minus 3/5 is going to be 2/5, because it's 5 minus 3 all over 5. And then we have a negative 4/5. When you divide by fractions, you multiply by the reciprocal. So 2/5 times a negative 5/4. The 5s are going to cancel out, just leaving 1s. And then the 2 is going to reduce with the 4 a little bit. So we have 1 times a negative 1. So it's a negative 1 over 1 times a 2, which is a 2. So it turns out to be a negative half. Now, again, just to check this, if we used the sine over cosine, that means we have the sine of theta over 2 divided by the cosine of theta over 2. We know the sine of theta over 2 is 1 over the square root of 5, and we know the cosine was a negative 2 over the square root of 5. Which is 1 over a square root of 5 times a negative square root of 5 over 2, multiplying the reciprocal. The square roots cancel, and so you're left with a negative 1/2. So it does come out to be the same thing, and it's probably a little easier maybe to do. But again, I just wanted to show you what it would look like if you did the identity. And we could have used the other version for the tangent, which is the sine over 1 plus cosine of theta. So there's different options you can take to get the answers here. One is no better than the other. It just depends on how you feel like approaching it. All right, so let's look at an example where we use the reduction identity. So we're given cosine to the 4th power of theta, and we want to write it with only first powers of cosine. So what that means is we basically want to get rid of all the exponents. We don't want to have any 4th, 3rd, 2nd powers. We just want to have strictly just cosines of various angles. This is kind of a tricky one. For those of you who are headed towards calculus, particularly Calc 2, it's something you'll want to keep in mind once you get there. But so how do we rewrite this? So cosine to the 4th power. What that really means is that you have another way you could write cosine to the 4th power of theta would be cosine of theta all to the 4th power. It's not the theta that's to the 4th power, it's the whole cosine of theta that's to the 4th power. And that means you have cosine of theta times cosine of theta times a 3rd cosine of theta and then a 4th cosine of theta. Now, that may seem like that's what we're trying to do, is write it as first powers, which I just technically did. There's no powers there. But I don't want the multiplications there, so we need to simplify this to some degree. Quite a bit, in fact. So to do that, we want to use our reduction identity, which the reduction identity requires us to have a cosine squared. So if we look at the first two, if we group these as one cosine times cosine and another cosine times cosine, each of those becomes a cosine squared. So we have cosine squared times another cosine squared. So squared times squared gives you to the fourth. This is where our reduction identity comes into play. We know cosine squared of theta can be rewritten as 1 plus the cosine of 2 theta all over 2. So that's the first part that's being squared. We also have the second part, so it's another 1 plus cosine of 2 theta all over 2. So we have these two parentheses, so we need to simplify this because we still have a multiplication here and we don't want that. So the first thing I would do is we have both of these 2's in the denominator, which if you multiply the denominators you get a 1/4. Okay. And then we're going to have to FOIL the numerator. So when we FOIL the numerator, 1 times 1, that's the first number, is going to give us a 1. And then we do the outsides. So we have a 1 times a cosine of 2 theta, so that's plus a cosine of 2 theta. We do the insides, which is a cosine of 2 theta times another 1, so it's just going to be another cosine of 2 theta. And then we do the last, which is cosine of 2 theta times another cosine of 2 theta. When you multiply something by itself, it becomes squared. So we have the cosine of 2 theta squared. And again, this is all over a 4, which I'm going to rewrite that here in a minute, but just because I like having fractions instead of a big fraction like this. That fraction, that fourth, goes to each term in the numerator. So we have a 1/4 plus, well, we have a cosine of 2 theta plus another cosine of 2 theta. So that's really 2 cosine of 2 theta, but it's divided by 4. So I'm going to just write that as a 2/4, or you could reduce that down to a half cosine of 2 theta plus a 1/4 cosine squared of 2 theta. Okay, we're almost there. That last cosine squared is the only problem that we have left over. So the 1/4 we can leave alone because it doesn't have a cosine to a power. The 2/4 cosine, you could think of that as just 1/2 cosine of 2 theta. Plus you have another 1/4. And we have another cosine squared. So how do we get rid of cosine squared? We use our reduction identity, which says you have 1 plus the cosine of double the angle, which we're going to come back to that here in a second. And then all of that's over 2. So what goes into my angle? What goes into cosine here? So normally the identity says you go from theta, so cosine squared of theta, that's 1 theta, to a cosine of 2 theta. So you're taking 2 times the original angle. Well, what if the original angle was already 2 theta? That means you're taking 2 times another 2 theta, which means we're actually going to have a 4 theta here. So that last parentheses is 1 plus cosine of 4 theta all over 2. All right, and so we have now written this without any squares on the cosine. They're all cosines. They do have double or even a quadruple angle, but that's fine. I don't care about that. So if we simplify, that's all we have left to do. We have 1/4 plus 1/2 cosine of 2 theta plus, so to simplify this here, I can multiply the 1/4 and the 2 in the denominator, and that's going to give me a 1/8. And if I distribute that 1/4 in here as well, we're kind of doing two things here in one step. That's 1/8 times a 1, so it's just 1/8, plus a 1/8 times that cosine. So plus 1/8 cosine of 4 theta. If we combine like terms, the only thing that are like terms right now is the 1/4 out front and then the 1/8. So 1/4 plus 1/8 would be 3/8. Again, common denominator for the 1/4. So 3/8 plus 1/2 cosine of 2 theta plus 1/8 cosine of 4 theta. And again, that's not the easiest thing to come up with, but that's the answer that we get. Okay, so we've been able to take cosine to the 4th and rewrite it so we no longer have any squared terms in there. So we're given sine of 5 pi over 12 times the cosine of 5 pi over 12. In the last lesson, we looked at how you could use the sum or the difference identities to rewrite 5 pi over 12, and we could do that here. So that's one option. We could also think of 5 pi over 12 as a half-angle identity. Because we know 5 pi over 12, if that was equal to theta over 2, if I were to solve this for theta and multiply both sides by 2, we would get theta is equal to 5 pi over 6. Okay, so I could do that. Not my favorite option though, because if you remember the half-angle identities, we have those square roots. And so I kind of want to avoid that if I don't have to use it. But if we look at the given problem, it almost looks like the sine of A, or we could maybe say the sine of theta, times the cosine of the same thing, angle A. So we have the sine of A times the cosine of A. Right? So have we seen an identity that has a sine of A and cosine of A? Well, sort of, yeah. I know 2 times the sine of A cosine of A is equal to the sine of double that, 2A. We talked theta in the actual definition, but so 2 times the sine of A times the cosine of A is equal to the sine of 2A. But there's no 2 in this problem. So if I know this is an identity, I know it's true, so I could sort of treat it like an equation. I'm not proving it. I'm just rewriting it. So we could divide a 2. So we could divide a 2 into both sides. So doing that means the sine of A times the cosine of A must equal 1/2 the sine of 2A. Okay, so that means the sine of 5 pi over 12 times the cosine of 5 pi over 12 must equal 1/2 the sine of 2 times 5 pi over 12. Okay, this is looking a lot easier than it would be if we did the half angle. So this is actually the double angle. So it's looking like it's going to be a lot easier to do this computation because I don't have to deal with those square roots. So if we simplify this a little bit, we have 1/2 times the sine. So 2 times 5 pi over 12 is really 10 pi over 12, which reduces down to 5 pi over 6. So what's the sine of 5 pi over 6? Again, pi over 6, well, we know the sine of pi over 6 is 1/2. But 5 pi over 6 is in the second quadrant. But we know sine is positive in the second quadrant, so this is still going to be 1/2. So we have 1/2 times the sine, which turns out to be 1/2, and 1/2 times 1/2 turns out to be 1/4. So the sine of 5 pi over 12 times the cosine of 5 pi over 12 turns out to be 1/4. All right, a second example, we'll say we have the cosine squared of 11 pi over 12. So looking at 11 pi over 12, again, that's not a unit circle angle, so we're going to have to do something to get rid of that 12 to reduce it down to a 3, a 4, a 6, or a 2. And we also have a cosine squared. And there's several identities. So one is the Pythagorean identity. So when you have a cosine or sine squared, that should be one of the first places we go to, one of the first identities, first things we think about. But that may not necessarily be the most helpful here. So we also have another identity that allows us just to get rid of that square. Okay, so again, there's a lot of identities you can look at. What we want to do is find an identity that works well, that makes life easier for us. And so one of those identities is our reduction. We know cosine squared of theta is going to be 1 plus the cosine of 2 theta all over 2. Okay. Now there's several reasons why I'm picking this. Converting the cosine squared to a sine squared, it doesn't simplify anything. It just changes the function. Okay. So the nice thing about doing this is it converts cosine squared down to just a cosine. But it also takes care of the theta. If I originally have 11 pi over 12, I'm going to take that 11 pi over 12 and multiply it by 2. And that's going to change that 12 denominator. So let's see what happens. So if we have cosine squared 11 pi over 12, it becomes the fraction of 1 plus the cosine of 2 times an 11 pi over 12 all over 2. Now, what happens when you take a 2 times an 11 pi over 12? The 2 and the 12 reduce to a 6. So that means we have 1 plus the cosine of an 11 pi over 6 all over 2. And that 11 pi over 6, again, is a unit circle value. So by using this reduction method, we've been able to convert an angle that was not a unit circle value into an angle that is a unit circle value. And just again, to compute the cosine of 11 pi over 6, we know 0 is the positive x-axis, 6 pi over 6 is the negative x-axis, and then if we kept rotating around, getting back to 0 would be 12 pi over 6, because that's 2 pi. So 11 pi over 6 has to stop just short of that, somewhere in the 4th quadrant. And what do we know about cosine in the 4th quadrant? It's going to be positive. So we're going to have 1 plus, what's the cosine of pi over 6? It's a root 3 over 2, and that's all over 2. There's a little bit of simplifying we could do here, but that's pretty much it for your answer. If you wanted to do, say, a common denominator, you could convert the 1 to a 2 over 2 plus a root 3 over 2. That's all divided by 2, which you think of that as a 2 over 1. So you're going to flip it around and multiply by a 1 over 2. So that would give us 2 over 4 plus a root 3 over 4. We're just multiplying everything by a 1/2. And you could even rewrite that as 2 plus a root 3 all over 4. Okay, so that's probably the nicest way that we could write the answer. All right, one more example, and then we'll be done. So say we wanted to compute the tangent of 3 pi over 8. It's not tangent squared, so we're not going to deal with the reduction identity. So we either have to deal with a 2 theta or a theta over 2. So let's consider both of those. So let's see if we had our double angle. So that means we're thinking 3 pi over 8 is equal to 2 theta. And to solve this for theta, you have to divide both sides by 2, which is going to give us 3 pi over 16 is equal to theta. And 3 pi over 16 is not a unit circle value, so we don't want to mess with that. So let's try half angle. That means 3 pi over 8 must equal theta over 2. So multiply both sides by 2. So you have theta is equal to 3 pi over 4. That is a unit circle value. So that's the route we want to take. And so we know that the tangent of theta over 2 will be equal to, and in this one we have a couple different options. Let's just do the first one. 1 minus the cosine of theta over the sine of theta. And in this case, theta is 3/4. So that means the tangent of 3 pi over 8 will equal a 1 minus a cosine of 3 pi over 4. So we changed it from 2 theta, or theta over 2, to just theta, all over the sine of another 3 pi over 4. So we just have to compute the sine and cosine of 3 pi over 4. So the cosine, so 3 pi over 4, where's that going to be at? So again, the x-axis, positive x-axis is 0. The negative x-axis is pi, so we could think of that as 4 pi over 4. Halfway, so at the 90 degrees, the y-axis is going to be 2 pi over 4. So that means 3 has to be in the middle here. So 3 pi over 4 is in the second quadrant. What do we know about cosine in the second quadrant? It's negative, and the cosine of a pi over 4 is root 2 over 2. What do we know about sine? It's positive, so we're going to have a positive root 2 over 2. So that means if we simplify things here, we have in the numerator 1 plus a root 2 over 2 all over another root 2 over 2. Again, that's pretty much our answer. We could simplify it. There's a few ways we could maybe try and do this. We'll take our root 2 over 2 and flip it and multiply. So we're going to multiply by 2 over a root 2. So that means you have to distribute that. So 2 over root 2 times a 1, which is going to be 2 over root 2, plus, and if you take root 2 over 2 times a 2 over root 2, everything kind of cancels out and you're just left with a 1. And then we could simplify this more. So just for fun here, 2 over root 2, if you rationalize, the denominator would be 2 root 2 over 2. So you multiply top and bottom by a root 2 over root 2. So 2 root 2 over 2 plus a 1, the 2's cancel, and you're left with a root 2 plus a 1. And so that would be the nicest, simplest answer that we could have. Homework would be fine with the unsimplified fraction. Tests, if you can, I think it'd pretty much be fine with unsimplified as well. You might have to simplify it some though, but so root 2 plus 1 would be our simplest answer there.